Basic electricity, direct current. Number 2, symbols, diagrams, and circuits. In the last program, you were introduced to the 4 principal concepts of electricity. They are electron flow, current, voltage, and resistance. You were also shown some shorthand for those terms such as I for current, E for voltage, and R for resistance. Now, in this program, you'll be shown more shorthand or symbols and different types of electrical diagrams. Finally, you'll see how to design and build a simple direct current or DC circuit.
To begin, here are some of the common symbols you'll need to know. For example, a wire or conductor is simply a straight line. The symbol for a power source, in this case you'll be using a dry cell battery, are sets of 2 parallel lines. Notice that one of the lines is shorter than the other. The shorter line represents the negative terminal, and the longer line represents the positive terminal. The power source symbol is always the same, no matter where or how it's positioned in the circuit diagram. Here is the symbol for a switch. An open switch indicates that the circuit is not complete, and consequently no current can flow. Whereas a closed switch indicates that the circuit is complete, and current can flow through it. This is the symbol for a light bulb or lamp. Now, with these symbols in mind, let's take a look at the type of electrical diagram in which they are used. It is called a schematic diagram.
A schematic diagram is a drawing of a circuit using these standard symbols to represent the various components. It tells you where and how the electric parts are connected in a specific circuit. In other words, a schematic diagram is the circuit's roadmap. In reading and drawing schematic diagrams, there are a few simple rules to learn. They are: 1. Schematic diagrams always use only electrical symbols. 2. Wiring leads from components in the circuit are represented by a straight line. 3. A heavy dot indicates a connection of 2 wires. In schematic drawings, the lines representing wires or conductors often cross. A dot indicates there is an electrical connection where the wires cross. However, if there is no dot, there is no connection. Also, a dot is not used if only 2 components are joined. For example, here are 3 batteries with the negative terminals connected, and no dot is used to indicate the connection. In addition to schematics, there are 2 other types of diagrams: wiring diagrams and pictorial diagrams.
A pictorial diagram is used to show the physical details of the components and the wiring connections as you would actually see them. The pictorial diagram is used primarily for the identification and location of components.
The wiring diagram is similar to a pictorial diagram, except that the components are shown as rectangles or circles. Wiring diagrams show the location or layout of components in their actual positions, along with the wiring used to connect them together. But of the 3 types of diagrams, pictorial, wiring, and schematic, it is the schematic diagram that's most commonly used. In just a few moments, you are going to put to work everything you've learned by building a simple DC circuit.
For the power source, you will use a 6-volt dry cell battery. So let's first find out just how your power source produces its voltage. The battery develops its voltage by converting chemical energy to electrical energy. The shell of the battery is a metal can made of zinc with a carbon rod suspended in the center of the zinc can. The rest of the can is filled with a chemical paste, composed primarily of zinc chloride. To create voltage, the zinc and carbon react with the chemicals in the paste, forcing electrons from the center rod to the casing. As a result, the zinc casing becomes negatively charged, and the carbon rod is left with a positive charge. Eventually, the chemicals are neutralized and no further reaction takes place. The chemical energy is depleted and you have a dead battery. As you probably know, you can also have a dead battery in your car. After all, it too works essentially the same way as a dry cell battery. The difference is, the automobile battery is made up of wet cells, which can be recharged. They're called wet because of a solution of sulfuric acid and water used to help create the charge, much like the paste-like material in the dry cell battery. Now, let's learn how to build a simple circuit.
First, look at your schematic. Every circuit consists of a power source and a load that makes use of that power. Both the power source and load are connected together by wires to complete the circuit. In addition to these basic components, you can add a switch that may be open to break the circuit or closed to complete the circuit. In this case, a single-throw knife switch. In order to build this circuit, you'll need the following tools: a screwdriver, long-nosed pliers, a wire stripper, and a diagonal wire cutter. To begin, cut several lengths of wire about a foot long. Roll out several lengths against a ruler, and then place the wire in the wire cutter. Turn the beveled side of the cutter down and squeeze. The reason you turn the bevel down is to protect yourself and anyone around you. Cutting wire can shoot a piece of it several feet with considerable force, and someone could get hurt. Always observe safety rules in order to prevent accidents. Next, you will have to strip away about 1.5 inches of insulation from the wire. To do this, first determine the gauge of the wire you're using. Then, tighten the set screw on the wire stripper. This set screw will keep the jaws from closing completely and let you cut through only the insulation without cutting through the wire. Once you're set, squeeze the strippers. This cuts the insulation, but not the wire, allowing you to slip the insulation off.
To connect the wire to a terminal, you must form a terminal loop on the ends of the wire. To make the loop, first grasp the bare wire near the insulation with the long-nosed pliers and bend it to form a right angle. Then again grasp the end of the bare wire with the long-nosed pliers. Now take your time and slowly bend the wire into a circle around the long-nosed pliers. Finally, cut away the excess wire, and you have the finished terminal loop. Whenever you connect the wire to a terminal post, place the loop over the post so that the rotation of the nut will wrap the loop around the post. The nut or screw tightens by turning clockwise. Place the loop so it wraps in the same direction. This will help to ensure that the wire is secure. In some cases, you'll have to fit the loop under or around a screw terminal. To do this, again check to be sure the loop is wrapped in a clockwise direction. Then use the long-nosed pliers to squeeze the wire together and tighten.
Now, to build your circuit, first connect a wire to the negative terminal of the battery. And with the switch open, connect the other end of the wire to a terminal of the switch. Next, use another wire to connect the other end of the switch to either terminal of the light socket. Finally, connect a wire between the other terminal of the light and the positive terminal of the battery. Now that the circuit is wired, take a bulb and screw it into the socket. To test the circuit, close the switch. Now, if the lamp lights, you've wired the circuit correctly. Congratulate yourself on a job well done. However, if the lamp doesn't light, open the switch and check all the wiring connections to make sure there is good contact at each point. Adjust and tighten any that look loose. And try again. There, that's better. Let's stop here and review.
Number 1. Symbols are commonly used to describe various components in electricity. You must become familiar with each of these symbols so you can easily read schematic diagrams.
Number 2. When cutting wire, always point the beveled side of the cutters down toward the floor. Cutting wire can shoot several feet and injure someone. Always work safely.
Number 3. When attaching a wire to a binding post, always wrap the wire in a clockwise direction. In the next program, you'll be shown how to properly read and use an ammeter and voltmeter. Then you'll see how to use them to take measurements of the circuit.